Natural language processing, or NLP for short, is another advanced application of AI. The goal of NLP is to build agents that can understand and produce natural language. We believe that the ability to use language is what sets us humans apart. Even our most beloved pets are not really able to understand us. When we tell Ginger, "Okay, Ginger, I've had it. You stay out of the garbage. Understand, Ginger? Stay out of the garbage or else." What does Ginger understand? Ginger hears, "Blah, blah, Ginger, blah, 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 Ginger, blah, blah, blah." So, why is it important for computers to understand and produce language? Well, it all started with the Turing test. We wanted machines that act like humans. And what better way to act like humans than to use the language humans use? Of course, machines that understand language can communicate with humans. They can become our personal assistants. But the most important drive to have computers understand language is learning. Most of our knowledge today is available in natural language. If we could get computers to read and understand all the books we have, we'll be set. So, what is NLP? The fundamental goal of NLP is to analyze and process human language broadly, robustly, and accurately. And today we have end systems that can recognize speech, that can translate, that can extract information from huge databases. We have dialogue interface systems, we have personal assistants. These end systems just a few years ago seemed very ambitious. Today we use them on a daily basis. The biggest challenge in NLP is the inherent ambiguity of natural language. Here are a few newspaper headlines that may have multiple interpretations. Enraged cow injures farmer with axe. Who had the axe? Was it the cow or the farmer? Hospitals are sued by 7-foot doctors. Are these really tall doctors suing the hospitals? Or are these foot doctors, 7 of them, suing hospitals? Iraqi head seeks arms. Are we talking about body parts here or weapons? Juvenile court to try shooting defendant. Why are they shooting the defendant? Stolen painting found by tree. Wow, how did the tree find the painting? And this one, I'm not going to say anything about it. Kids make nutritious snacks. A context-free grammar is a set of rules that describe the syntax of a language. For instance, we know that a sentence can be made up of a noun phrase followed by a verb phrase. A noun phrase is a determiner followed by a noun, or it could be just a noun. A verb phrase is a verb followed by a noun phrase. A noun can be a dog or can be anything else. So we have a bunch of these rules and we try to parse language based on these rules. So we end up with a parse tree, such as this one. When we have a sentence such as "the dog ate the bone," we parse it and we end up having a noun phrase followed by a verb phrase. Here, the noun phrase is "the dog," and the verb phrase is "ate the bone." So parsing can be viewed as a search. For instance, we have the sentence "Hershey bars protest." We can parse that as a noun phrase, Hershey, followed by a verb phrase, bars protest. And with this parsing, we understand that Hershey, the company Hershey, bars protest. Or we can parse it as a noun phrase followed by a verb phrase where the noun phrase is Hershey bars and the verb phrase is protest. And the meaning associated with this parsing is completely different. It's the Hershey bars that protest. So these two parse trees are possible. Our goal is to find the best parse tree. Which one of the two is better? To make that decision, we introduce probabilities to our model. So instead of a context-free grammar, we base our parsing on probabilistic context-free grammars, or PCFG for short. Each rule in the context-free grammar has a conditional probability associated with it, and a parse tree's probability is computed from the probabilities of all the rules used. So let's say this parse tree uses the following rules, right? So each one of these rules has a probability associated with it. And to compute the probability of this parse tree, we basically combine the probabilities of the associated rules. And then we pick the parse tree associated with the highest probability. So parsing becomes a search here. We find the parse tree with the highest probability. So we associate an inverse probability with cost. We want the highest probability or the lowest cost. And then we can use A star search to find the best parse tree. Of course, we need a good heuristic. So where do these probabilities come from? They come from data. Now, parse trees are not readily available. Parse trees have to be manually created. Luckily, the research community invested in tree banks. The Penn Tree Bank is one of the first large tree banks. It took about 8 years to complete, and it's widely used today. So if you're interested in natural language processing, Python has the right toolkit for you. NLTK is a Python package for natural language processing. It includes interfaces to NLP resources. It includes text processing libraries for classification, tokenization, tagging, parsing, and semantic reasoning. We can't talk about natural language processing without talking about dialogue systems. Dialogue systems are intended to converse with humans, and dialogue systems have come a long way since the early days of AI. The first dialogue system we had was called ELIZA. It was created in the mid 60s. ELIZA was supposed to emulate a therapist that does not give you the right answers, but helps you find the answers for yourself. ELIZA was basically performing some basic pattern matching. It was picking up on some keywords and responding with answers that included these keywords. For instance, when the user would say, I remember so and so, ELIZA would respond, do you often think of so and so? Then came Watson. Watson was able to answer questions in English. He competed against Jeopardy champions and won. Now, Watson used some sophisticated NLP with a deep analysis of questions, noisy matching of questions to potential answers, and lots of data. Watson had over 90 servers doing computations. Today, we have personal assistants everywhere. We have Siri, Alexa, Google. IBM Project Debater is an AI that can debate humans on complex topics. You can check it out online. And now we come to the end of our course. It's a good time to ask the question, what if AI succeeds? What will the world look like if we are successful in AI? Will we end up in a perfect world where we have time to pursue our interests and all our day-to-day tasks are performed by robots? Or will these robots pose an existential threat? Stuart Russell is one of the authors of our textbook. He is also a professor at UC Berkeley. He has raised concerns about AI. He has narrated a very scary short movie called Slaughterbots that highlights the dangers of autonomous weapons. He has been advocating for safer AI. I have included his TED Talk Three principles for creating safer AI in today's lecture material. Make sure you watch it next.